This is how DeepSeek v3 has positional embeddings for each token coded. So we will understand this rotary positional embeddings and how they code and mathematics behind it and logic and how they apply it in DeepSeek v3. The required knowledge you should have before watching this video is about tokens, position embeddings, maybe somewhat around transformer architecture, but maybe that's not necessary. So if you don't understand these things, if you hear them for the first time, you can watch videos on YouTube like my video here, coding DeepSeek from scratch, and you can search for videos like RoPE explained, RoPE, RoPE explained, rotational positional embeddings. But I will also be explaining it now. So let's start. So if we have a vector embedding for a token, vector embedding is just an array of numbers. We need to encode positional information of that sentence. Let's say this is the sentence. So for each token, maybe this is one token, this is one second token, this is third token. Position, so this is the first one, the second, the third. And we're gonna use RoPE, rotational positional embeddings or encodings, I think, to encode position. And this is how we will do it. This is the code. So first we will pre-compute these frequencies, which is just pre-computing for each position how much to rotate the embedding vector. So depending on how much we rotate the embedding vector, that's how we will pre-compute, that's how we will know the position. And we will not just rotate the entire vector, we will rotate each pair of numbers in the vector. So the vector should have an even number of elements, so we can rotate each pair. And we will rotate each pair differently. So I will put this ChatGPT conversation, this article below, and you can, I feel like these videos are mostly for self-studying, so you can follow what I'm talking about, but you will definitely not understand everything. So you can copy this article or ask questions to ChatGPT or another AI. So we can start here. So first we will define some hyperparameters, and what's important, query and key RoPE head dimension is 8. So DeepSeek v3, it has part of query and key rotated RoPE, and another part is not rotated, so they call it nope, not rotate. So this part of query and key that is rotated is 8, but in DeepSeek v3 it's a lot bigger. This is just an easy example. And then training sequence length is 4 tokens. Usually it's like 10,000 or 4,000 tokens, and later extended, but they just 4 tokens now. Validation sequence length. In validation, we can use more tokens because we need less memory than training. So we can just bump up number of tokens. This is the rotation angle that we start from. We're going to adjust this angle based on position of token and position of the pair in the vector embedding. And we have some variables. We'll see what these mean. I think I've read about them, but let's see. This is the first line of code. We need to generate these frequencies. So let's first take a look at this part. This is the part that executes first, I'm pretty sure. Okay, so dimension is 8. We will create a tensor, and that tensor will be type float 32. And I talk about types in my last video. If you scroll here, FP8 quantization, you can learn there. And then we are starting from 0, including 0, to dim, which is gonna be 8. So from 0 to 8, and going by 2. So we will go 0, 2, 4, 6, and 8 will not be included. That's how it works. So if you have torch arrange this, it's written here the same thing. 0 to 8 with step 2, you will get this tensor. 0, 2, 4, 6. So that's how this works. And then we will divide this by the dimension. That's the second thing that's going to happen. So we divide each element by this 8. So this is to normalize between 0 and 1. And then we will raise base 1 over 10,000 to these powers, and base 10,000. I think that this is it. This is the RoPE theta that we have. That's the base, the RoPE theta angle, base angle. And now when we raise 10,000 to all of these numbers, we will get our angles of rotation. And as you can see, because we normalize it between 0 and 1, we will get numbers smaller than this 10,000. So now what we did is we just got the array of angles, how much to rotate. So now this is just okay, these are base powers. Okay, so these are not rotations yet. So this is the frequencies. The rotations are here. 1 over base powers. So we divide 1 with each of these. So now these are the frequencies. And so we will use these numbers depending on the position of each element in the head, RoPE head. So these are individual elements, or I think pairs of elements. Let's see. Okay, we just got these numbers, array of numbers for rotation. Let's see what happens next. Okay, all we know for now is that we got these numbers, but what are we gonna do with them? I don't know, but we know how we got them and we understand this first line, how it works. That's gonna be this line in our code. And next we are gonna see if the current sequence length is larger than the sequence length we trained on. So that's gonna happen if our eval or test time when we are generating sequence length is larger, then we need to scale. So if we just trained the model to 4,000 tokens, but we have 8,000 context window, we need to scale our row positions to include tokens up to 8,000 positions. So to continue, let's first understand this. Rotary Positional Embeddings, or RoPE, inject position information by rotating query and key vectors in the complex plane using e to the power of I theta, where theta depends on position of the token and a set of frequencies omega. And this set of frequencies omega is what we just calculated, this array, and it will be same for every token. And for every token, it will determine how to rotate each pair of the dimensions. So let's say token embedding has 756 numbers or elements or dimensions. All we can use those terms interchangeably in this case. So we will have 756 divided by 2 frequencies, and we will use one frequency for each pair. So number of token, and so theta, the angle of rotation, is gonna be equal to the number of position of token times, or this is omega d, for each position t and dimension d. So this is gonna be our number in our array that we just calculated, array for the dimension pairs. Lower frequency dimensions rotate slowly, higher ones rotate faster. This is done by design. So the AI learns when it sees slower rotations that those are smaller dimensions, like in the beginning, the first, second, third dimension. And bigger rotations are gonna be towards the ending elements, ending dimensions of the vector embeddings. Okay, so we have this parameter number, and by the way, this video, I kinda imagine it that it will just help you determine what to self-study, because this is tough, especially if you don't, if you never work on this, or this is the first time you hear this. So you can continue asking ChatGPT for a couple days probably, or learning this for a couple days that I'm explaining. So we have some issues here. Dimensions that are towards the end, that are going to rotate very quickly, that we will rotate very quickly. The quick rotation will cause some poor performance. So papers like Yarn or XPOS position, which show that high frequency components cause poor extrapolation. Extrapolation is when we extend from the training length to extend to whatever the size. So we've trained on 4,000 tokens, we want to extend to 8, 10, 16, whatever. So if our rotations are rotating too quickly, that will cause problems. So we need to reduce those rotations towards the end positions that rotate too quickly. So we can find frequencies that rotate by 2 or more times, and those are fast rotations. So we will scale them down using this RoPE factor. So we will scale the frequencies towards the end by this RoPE factor, because they will rotate too fast. So let's read the summary. Number of rotations is how many full 2 pi 360 degrees turns a dimension completes across sequence. So what does this across sequence mean? So as I said, we have formula number of tokens times this omega. So this is the rotation angle. And the higher the token number, as you can see, bigger multiplying product, we will get bigger rotation. So as I said, for the rotation angle is calculated by the token position, token index, and for each of the pairs of the dimensions in the embedding, so each number pair has its own rotation angle as well. So over the entire sequence, when we get token with index 0, this will be 0, so the angle of rotation will be 0. And the last token will have sequence length minus 1 times omega. So that's gonna be the last rotation for the last one. And this omega is, as I said, a vector, a tensor for each of the pairs of the elements. So let's quickly take a look at omega here. So omega is a vector. We will return. So more precisely, it's a set of frequencies, one per each dimension pair, since RoPE operates on pairs of dimensions. So how omega is used? Assume your embedding size is 8, then RoPE acts on dimension over 2 equals 4 pairs. So the first pair will be first and second element, second and third and fourth element, etc. For each pair, I and I plus 1, we assign a unique frequency, omega I. So our omega is going to be an array of frequencies for each pair of these elements. So at position t, the rotation angle for each pair is t times omega. Then the pair x of 2i plus 1, and It's 2i because it's because of pairs. You can think about it why it's 2i. Uh, so now we have the position. So this is actually just the classic linear transformation, the matrix, the linear rotation, the matrix. So this is the matrix, rotation matrix. And rotation matrices, you can watch videos on YouTube. I actually have a video about it as well. If you just search for RoPE on my channel. But basically this is a matrix that will rotate this vector. And we will get this new rotated vector. And I have explained this well, and you can also ask AI to explain. I have a good video, and there are other good videos on 2D rotation matrix and how they rotate the vectors. Well, actually, you can represent this same rotation this way. So you have the first element of the pair and the second element of the pair, x and y, and you turn it to or you treat it as imaginary number. So now you take this complex form and you multiply with e to the power of this imaginary one, I, times omega I. And this can also be written as in this format. And if you remember, oh, this is theta, sorry, this is theta. If you remember, theta I is equal to the token position times the angle for this particular pair of values. So we do this for every pair of values. I guess this just requires self-studying. This is a bit messy or complex, but in a couple of hours or days, depending, you can learn it, depending on your previous knowledge and experience. And we can check out our first line of code again. So now we can understand these are omega. This is omega array. This gives a decreasing frequency scale like in Fourier features. Lower dimensions rotate slowly, so the beginning, the left numbers dimensions rotate slowly and higher dimensions rotate faster. And now we can return to the beginning and just continue where we left off. So we have these hyperparameters. If we have these raw frequencies for each pair, we need to now, based on also the token positions, calculate this frequency matrix. So for each token, we will calculate how much to rotate each pair of that token. And this is the calculation. The first token is 0 times this entire vector. And then 1 times this entire same vector. And then 2, and then 3. So that's how we get all of these vectors for each of the tokens. How much to rotate each of its pairs of elements. Then what we need to do, if you see this formula, we then turn each entry x into e to the ix, which is calculated also as cosine of x plus I sine x. Writing each as a pair real imaginary, we get the following table. So here, these are the tokens, token number 0, 1, 2, 3, and these are the dimension numbers. So this is t, this is omega. And we are using this formula, cosine of t omega plus I sine t omega. So we will get these pairs. These are supposed to be a real part and the imaginary part, and real part and the imaginary part, etc. And we will use these pairs to rotate pairs of tokens, pairs of, no, not pairs, pairs of elements in token vector embedding later. We'll see what I mean by that. So this formula is done with torch.polar and torch.once like angles and then angles. So angles, it's gonna be this t times omega, and omega is a vector, as I said, and t is also a vector. So for omega equals, or this is theta, sorry, it's theta, equals 1, we get these values. And if you remember, we calculated omegas here. These are our, or thetas, oh my god, thetas. So we say t times omega, or angles, we get thetas. And now for each of the thetas, we calculate our frequencies. So if I scroll up there to the previous matrix, you see here, we know that x, this formula, we know that x is omega times t, and these are omega times t here. So we just put this instead of x, then this, then all of these one by one. These are all omega times t, and then calculate this matrix, and it will contain, it will be cosine and sine. So it's cosine and sine of x, of these numbers here. Let's take a look at this part. Torch polar, torch once like. What does this do? So the goal is to convert the real valued matrix of angles into complex valued matrix of unit vectors. And here we have angles. So angles is our big matrix. That's t token times omega. So step 1, understand the input angles. Angles is a 2D vectors tensor where rows are time steps t, or tokens t. Columns are frequencies omega k. And then each entry theta is t times omega k. So here. And then we have these torch once like angles. So this will create a tensor that's filled with number 1 and the same shape as angles. So in this case, 3 times 4. Why ones? We are creating complex numbers with magnitude 1, unit vector. And then we have torch polar. So we pass in magnitude and angle. This function converts polar coordinates to complex numbers. So if we have r as magnitude as and theta as angle, this will be equal to r times e to the I theta, which is r times cosine theta plus I sine theta. This is the classic formula. Since our magnitude is always 1, we just have that e to the I theta is equal to cosine theta plus I sine theta. We initialized it to be always 1 to make this easier to compute. So now when we pass this ones matrix and our angles, it gives a complex tensor of the same shape where each element is a unit complex number pointing in the direction theta. So if we take a look at this code again, so we create matrix of ones that's shaped like angles, and we pass in these actual angles. And again, angles are just t times omega. So these are our matrix of rotations. And so when we say torch polar ones and angles, we get this as our output. So this is the cosine part, this is the sine part, or real part, imaginary part. And we have for each of these based on this omega. So this is sine omega. So the final output, our frequencies, a tensor of shape, sequence length, which is going to be 1, 2, 3, and dimension over 2, integer division with 2. So we have 1, 2, 3, 4 elements, but the dimension was 8. But you see, each of them has two numbers for two the dimensions, because we will apply this number to the first dimension in the pair and this number the second dimension in the pair later. And finally, now that we have those frequencies pre-computed, let's see how we apply them, how DeepSeek applies them to the tensors, the actual tokens. Let's walk through your apply rotary embedding function step by step with a simple explanation and small example. Purpose. This function applies the rotary positional embeddings, or these frequencies tensor, to an input tensor X, typically the query or key tensor from attention. And it's gonna be both query and key in DeepSeek v3. So DeepSeek v3 has special query head and key head that are for RoPE, and then key heads and query head that don't have RoPE, and they get concatenated later. But that's besides the point. Let's see how this gets applied. So we have X shape, so batch, sequence length, number of heads, head dimension. And then we have head dimension must be even, since we rotate pairs of dimensions like 0, 1, 2, 3, etc. And then frequencies shape, it's gonna be sequence length and head dimension, so this head dimension divided by 2 with integer division. But this must be a pair even, so it will be normal division basically here. Or will be reshaped to match this. Yeah, this can also be reshaped, so this needs to match this shape. So head dimension over 2 and sequence length must have these. So we will get this float value of our tensor and make it contiguous, so it's in the memory, it's not broken up within the GPU memory. It's like all of the values are next to each other, the whole tensor. And this is not code by DeepSeek, but this is my code because I was trying to fix a bug. But I think this is, I'm pretty sure this is the same thing, so you should also know how to do this. And we will have it in float 32. That's for the complex calculations, because float 16 wouldn't have as much precision. So we calculate in float 32 and accumulate, and then later we can store in memory in brain float 16 or FP16 or whatever. And it needs to be contiguous because of the view operation that we have later. Now we have this float and we need to change its shape. So view, we will reshape it, and this will point to it in the memory. What is this asterisk? I forgot. Anyways, maybe we'll figure it out later. Okay, so we take the shape and we go from the first shape dimension to the last, but excluding the last. So we will copy the first dimension, so batch and sequence length, but then we will do something with the last dimension. So we will split last dimension into these two. And the reason I know we are splitting last is because here we are going from the first until the last, but excluding last, so those will be copied same. But then this last we will split, because there is only last left and we have these two, so it means last will be split. And it will split in a way that now the last dimension will have two elements, so these are our pairs. And then this will be filled, whatever. So depending on the actual size of this last dimension, we will split it into two, and then whatever the number of pairs is going to be this second to last dimension, whatever the amount of pairs. So if we have this dimension to be 700, then it will be 2 and 350. Okay, so what does it do? Treats each pair of dimensions as a real imaginary pair. For example, if head dimension is 8, it becomes 4 complex numbers. This is an example. So we have some batch, and inside of that batch there are multiple sequences. And if we look at just this token, yeah, this is one token. So I guess there would be one more dimension here, but this example doesn't show, but there would be batch, sequence, and tokens. So, okay, so this is the token, first dimension, second, third, fourth. And then when it's reshaped, you see we create pairs. And now the number of pairs is 4, and each pair has 2 elements. And so this X complex, we have torch view as complex, Z shaped, so it will convert it to complex numbers where I can show you real quick what this torch view as complex does. So if we have this tensor, it has one pair, second pair, third pair. If we pass this tensor through view as complex, we will get this tensor that has this like 1 plus 0j. So this is a tensor of complex numbers. And this is its shape, 3. So it's a complex tensor. And a complex tensor is nothing more than a real tensor of shape n and 2. So if you have a tensor of shape n, let's say it has 3 complex numbers, it's basically just represented as a real tensor of shape n and 2, so in the memory. So just those 2 numbers will be like represented in pairs in memory. I'll scroll to this so you can take a look, but it's just represented as a real tensor or vector. So then we will broadcast these frequencies. So view as, so we add the batch dimension and we add head dimension. And it's just one head. I think it's because they only have one head for both query and key that has RoPE applied to. So, but maybe we can look into this, like how they applied these ropes to these heads another time. This is not less important now. Okay, so we have batch dimension, head dimension. Why just one batch? I guess they are processing batches one by one. They are applying these frequencies to batches one by one, so you just need one batch dimension. And step 4, rotate via complex multiplication. So y complex is x complex times frequencies. And if we go a bit up, we see that we converted our x input to this x complex number, which is just grouping the last dimension into these pairs and nothing else. I'm 100%, 99% sure. So this is going to, the step 4 is going to multiply each complex number by a unit vector e to the I theta. This rotates each of the pairs by an angle depending on its position. Take a look at this example. So we have a pair 1, 0 in our x, and we have the frequencies, these two. So this is how, if we multiply those two, we get y complex. So 1 times the first frequency minus 0 times the second frequency. So we will get this real part, and the imaginary part is the 1 times and plus in between. So the new pair will be this real and imaginary part. So now let's see why we have this formula like that. So the formula for complex multiplication. Let's say we are multiplying two complex numbers, a ib times c plus id. The product is, this is the product, ac minus BD. So that's just the formula of multiplying these two numbers. And that's the formula. And I think I messed up a little bit up there when I was explaining it. But anyways, now you see the true formula. So why this formula? There is all of this mathematical derivation, some more explanations, and this is our rotation matrix, by the way. This rotates a vector. So if we are multiplying some vector with some complex number that can also be represented as this, then we have this multiplication. And if we multiply each of these pairs, you'll see that you are actually multiplying this guy with this matrix. So that was just about multiplying two complex numbers. You see you have this and these are same, and then this and these are same. So then we will convert back to real numbers. So we will just do torch view as real. So this will, I think this will literally, I mean, they will still stay pairs, but now those pairs will be just like represented as real numbers. Whatever, doesn't change anything. I mean, even the complex numbers, they are saved in memory as real number pairs as well. They just have maybe some additional markings telling the Python that these are should be like seen as complex numbers. And we will flatten at the end. After we convert it to real numbers, we will flatten the last dimension, the third dimension. So we go from, you know, the pairs and the number of pairs, two dimensions into one dimension, which will just be head dimension. And then in the end, we just convert to D-type back. So it was the original type that we saved. So I think that's it. I'm gonna leave you a link. I'm gonna share this whole conversation so you can self-study. This video is, you can watch these videos to self-study because this is a complex topic. You will need days, probably, even weeks. I don't know about weeks, but days for sure. And now we know how to calculate and apply these frequencies, pre-compute frequencies, and apply rotary embeddings in DeepSeek paper. You can check my channel for more content about this. You can learn about DeepSeek, quantization, everything about DeepSeek models, coding it from scratch, and a bunch of this. And you can also check my Bilibili, but I don't know how to share. Like, I don't know if this is my name. I don't know any of this. I'm just posting some videos here. I'll figure it out eventually. But it's same videos as in YouTube. I think I have a bit more on YouTube as well. Thank you for watching. You can follow my channel if you wanna learn AI research science, NLMs, and engineering and stuff with me. So see you in the next video.